Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video discusses some important considerations when designing experiments to conduct one-way Anova testing, as well as how to determine which sample mean is different from the rest with the Bonferroni test. Let's get started. So first, let's have a little discussion about designing our experiments for our statistical studies. The one-way Anova test allows us to test means from more than two populations. So we can continue to add more and more populations to our test. But doing that increases the potential influence for extraneous factors on our results. Because sometimes, and in fact more than sometimes, oftentimes you get interactions between the different groupings that you're testing. Naturally, we want to reduce the effect of any of these outside factors from our experiments. And so to do that, there's two design approaches that work really well for that. The first is a completely randomized design. In a completely randomized design, each sample value has the same chance of belonging to each of the different factor groups. The other way to go about it is with a rigorously controlled design. And with a rigorously controlled design, that means you're choosing sample values carefully so that all the other factors have no variability. And the details for that depend upon the context of what you're looking at. But generally speaking, you're going to arrange it so that you choose the samples to reduce the variability. Now, how is it that we're going to look at which actual mean value is different from the rest? Because as we've seen in previous mini lectures, the one-way Anova hypothesis testing method can tell us whether or not they're all the same or if one of them is different from the rest. Well, it could be at least one, but it could be more than one, and we don't know which ones are the ones that are different. So is there a way that we can have a statistical test that gives us statistical evidence as to which one or which ones are different from the rest? And there's different ways to go about it. We looked previously at some informal methods to do that. And we can just look at the sample means by constructing box plots to see where the box plots are relative to each other. We can construct confidence interval estimates for the means, then compare where the confidence intervals line up with each other, looking for regions of overlap, just like we were with the box plots. So there's different ways to go about it. But what we're looking for, specifically is a formal method, something that gives us statistical evidence that say, yes, not only is one of them different from the rest, but it's this one from the groupings. How do we do that? Well, we can do a range test, and a range test allows us to identify a subset of means that are not significantly different from each other. Much more common, though, is to use a multiple comparison test. So basically what we're doing is we're taking the mean values out in individual pairs, and then we run a test on those individual pairs. Okay? We have to make some adjustments, however, when we do this, because when you take stuff off in pairs like this, there's an adjustment you have to make this to the significance level, because the number of individual tests that you're running is going to be greater. And so depending upon how many groupings you're going to be comparing, you've got to make an accordant change in your significance level to accommodate the multiple tests. Now, by far the most common approach when you're doing multiple comparison testing is an approach called the Bonferroni comparison test. And so we're going to be looking specifically in the rest of this mini lecture at the Bonferroni test. To conduct the Bonferroni test, first you've got to get your sample pairs that you're going to test off with each other. Okay? So there's going to be a separate null hypothesis for each one of these sample pairings. Of course, the null hypothesis, being a statement of equality, says that they're just going to be equal to each other. But you got to have a separate null hypothesis for each possible pairing. Then you're going to calculate the test statistic, which is a t-score. Because, again, you're looking at two samples that have been paired off with each other. And remember, one of the assumptions that we're making with our methodology is that they're independent. Well, independent comparison of two sample means is going to give you a t-score for a test statistic. But the way we calculate it is a little bit different, as you can see here on the screen. So StatCrunch will not actually give you this t-score directly. However, it will give you all the numbers you need to plug into this formula to calculate the t-score yourself by hand. Next, what we're going to do is find the critical value or the p-value. And of course, as I said before, we've got to make some adjustments there because we're conducting multiple tests on multiple groupings. But I'll show you how to conduct those adjustments here, I think in the next mini lecture. And then once you get through that, okay, remember the critical value is going to be the boundary for your critical region. And then the p-value is going to be the two-tailed area in your student t-distribution. So it's just kind of different. So the critical value is coming from the critical region alpha with your student t-distribution, but you've got to divide alpha by the number of possible pairings of two samples. So if you're comparing 3 sample means, then you're going to have 3 different possible pairings. The first with the second, the first with the third, and the second with the third. So you've got to divide alpha by 3 to get the significance level that you use to find the critical region. The p-value then, but that's just on a one-tailed test, I think. And then the p-value is going to be a two-tailed area with the same student t-distribution, but it's bounded by the test statistic. Here's the kicker. You got to multiply the p-value by the number of possible variables. So with the critical value, you're dividing. With the p-value, you're multiplying. In either case, your degrees of freedom is going to be the total sample size. So you've got all the samples added together to get you a total sample size minus the number of groupings that you got. Once you've got those values, then you can resolve your hypothesis test just like you've always done using the conventions we're familiar with. And that's all there is to it. So that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.